Good afternoon. This week you are dealing with light and molecules. We have discussed this quite a bit here in lecture about absorption spectroscopy, and you are measuring the effectiveness of a sunscreen by measuring the absorption of the active ingredients of a sunscreen, and you measure the molar absorptivity. Also in your book it's called, not in the book, in the manual it's called the extinction coefficient. Extinction coefficient is an old expression, it's molar absorptivity, okay? If you look in your book, in your textbook, it's molar absorptivity. And so what kind of absorption do you expect there? What wavelengths would you need to measure the absorption of these ingredients of a sunscreen? What kind of wavelengths would that be? What kind of radiation would that be? UV radiation, okay? And there are several kinds of UV radiation, so you can't see it with the bare eye, but it's going to sap you, okay? So you need UV absorption spectroscopy, UV visible absorption spectroscopy. Bayer's law, this is the law that gives you the relation between the absorption, the length of your cell, the concentration, and the molar absorptivity. A equals epsilon times L times C. And then you also need to do dilution calculation. There was another thing I heard. There was last Monday, there was a midterm, was there? Okay. And so actually you did quite well. Except those who didn't feel that they were doing well. But there was a total of 120 points to be had, and the mean was 93 points. That's pretty good. And there were actually 3 students who had the total perfect score, all right? And so the grades are going to be posted this afternoon, this evening, and also all the solutions, including the detailed math for the, yes, ma'am? I do not curve anything, okay? We are not curving. You will get certain amount of points, and if you have read the B-space announcements, these points add all up, and at the end you can have 1,000 points plus 50 points that you get here, but just by sitting here and clicking that white thing, okay? Even doesn't matter if the answers are wrong or right, and you get 1,050 points, but with 1,000 points you have a super A, and the grading is given on B-space on several occasions. It will tell you the grade. So let's give you some more points, huh? Let's see, I gotta switch this off first. Okay. That doesn't do it, okay? You are wondering why I'm doing this. So now you can see that. Good. So now we're going to give you some bonus points if you can answer that question right. And so I would highly recommend that you take out your eye clickers and be very quiet and don't talk to each other and switch on your brain, especially if you have a picture in front of you. Look very closely at that picture. What it says there, exactly at the picture. Look very closely at it. And then try to give me the answer, but not the answer from your neighbor. That's not a discussion section here. All right? Let's go for it. Okay. None of the above. The question is, which energy level diagram corresponds to the observed spectrum shown here? This is the spectrum here. And is it A, B, C, D, or E? Look very carefully and give me your answer. Oh, I've done 1,000 of those. It's not true. I think you never did one of those. Exactly one of those. Uh-oh. No batteries? Need some batteries? I usually don't give out batteries. Maybe I'm not going to do this, otherwise everybody asks me for batteries. Look very carefully. Okay. So the right answer was this here. Okay. And why is that? Now you've seen many of those I did in front of you. They had these bars here, and I always went from left to right with increasing wavelengths, and from right to left with increasing frequency. What does this do? It's the opposite. You have to look very carefully, okay? What's the highest energy? Which one has the highest energy? This one here, okay? And what's the second highest energy? What you do, you turn it around. If you turn it around this way, then you have the spectrum actually, because the highest one would be up here, so we would have two double lines, and then one line this. You go from here to here, and from here to here, and from here to here. So you get exactly, if you turn this 90 degrees, you will see that it will look like this. So we have in the higher energy the two double lines. You got to look what's there. We never plotted nu there. We always plotted lambda, but this is why lambda stands here and nu here. Why nu stands here and lambda here. Okay? Where is it? What happened here? Okay. This was the answer. Okay? There was a little bit of thinking involved, not mechanically doing. All right? So, after this shock, we're going to go on, and I have to close that iClicker first, and then we start it. Otherwise, we don't know who got these points. 43, that's 8% of, no, 220, 43, that's about 20%, huh? Okay. No, less than 20%. Oh, that's not good. Better than on the test. That's good. So some people learned it, obviously, or they are concentrated in this room here. All right, now let me start that iClicker again. To get your participation points. Okay, good. There we go. And we're going to talk today first about what we did last week, or no, what we did on Monday. Where is it here? That's good. So on Monday, we introduced, today is Wednesday, on Monday we introduced the fourth quantum number, the magnetic quantum number, which is the fourth quantum number, the spin quantum number, m sub s. We knew already about m sub l, m sub s. And so I told you and I explained to you, if you have classical magnets, you have one here and another here, and you move one, the other one moves. And it moves fully in space, okay? Any way you move it, it will go with the other one. And if you have a whole bunch of them, they will all follow each other. Not so electrons. Electrons are quantum magnets, so to speak. They only can have half integer spin, plus 1/2 and minus 1/2. Plus 1/2 we can call upspin, and minus 1/2 we can call downspin. So there's nothing like this. There's only up and down. So we have two possibilities, up or down. And we then have now, we have our whole orbital model together by having defined the force quantum number, the spin quantum number, and with this we can see Pauli's exclusion principle. That means that no two electrons can have the same set of quantum numbers in the same orbital. So if you have, for example, a 1s orbital, how many electrons can you put in there? 2, because for this n equals 1, L equals 0, this is 0, and this can be minus 1/2 and plus 1/2, okay? So it has to be minus or plus, so we have 2 electrons. Becomes clearer when you have n equals 2, then L equals 1. So what is that? What kind of orbitals are those? P orbitals, okay. Now you have m sub L that can be minus 1, 0, and plus 1, so you have 3 p orbitals. And each p orbital can have how many electrons? 2, plus 1/2, minus 1/2, all right? So if you have, how many total p orbitals do we have? If, for example, 2p, how many total p orbitals do we have? 3. How many total electrons? 6. How many total d orbitals do we have? We are now in 3. 5. How many electrons? 10. Okay? That's what Pauli's principle says. Okay? Can have the same, no two electrons can have the same set of quantum numbers. What I said, n and L was the same for 1s, but m sub s, the spin quantum number, was plus 1/2 and minus 1/2. Okay? So with this we know that each orbital can have a maximum of 2 electrons. Not each level, each orbital in a certain level. Good. So now we're going to fill in electrons. We build up elements by filling in protons. You know, we do this automatically, but now we are interested in the electrons. We fill in the electrons. And we call this the build-up principle. Actually, it's a German word. It's called Aufbau principle, build-up principle. And so many words in quantum mechanics have some German origin, because most of these guys were German who came up with all this stuff. And with quantum mechanics, the founders of quantum mechanics, many of them were of German origin or Austrian origin who spoke German, and so they used this funny language to describe these things. And Aufbau principle is a word, an English word. So is also Bremsstrahlung. That's with radiation, that means breaking radiation. But this you don't have to know yet. So this is a cartoon here. Why is this a cartoon? Because I'm writing 2s and 3p and 3s, the quantum levels, the energy here, all next to each other. Okay? We know now that the 1s orbital is lower in energy than the 2s orbital, and the 2s orbital is slightly lower in energy than the 2p, and the 3s orbital is even higher in energy than the 2p. Okay? So I would have to stagger this here. But we know all this, and we make a cartoon. We just want to fill in electrons. Yeah? So don't get fooled. This is not all the same quantum level to begin with, and the same energy, the same ground state energy. So we have hydrogen. You see, we go over to the periodic table here, and I go back and forth between the periodic table and this here. So we have hydrogen. Hydrogen. Okay. They fixed the light, but it's still pretty dark down here. Look how fast. Maybe this works better. Yeah, this works better. Yeah, it works somewhat better. My God, I should drink more coffee. So this is hydrogen. We have 1 proton and 1 electron. And the electron is in the 1s orbital. We talk about ground states. And so we have 1 electron there. It's in 1s1. So if you have unpaired electrons, you have a magnetic momentum. They are paramagnetic. You have paramagnetism. If you have paired momentum, paired electrons, you don't have a magnetic momentum. That we call this diamagnetism. So if you bring them close to a magnet, they will react like a magnet, so to speak. Now we go the second one. Helium is atomic number 2. We put the second electron in. Now this goes anti-spin, so there's upspin and downspin. So helium is a 1, n equals 1, and an s2 configuration. Now this here, they cancel each other, these spins, in terms of magnetic momentum, and so they don't have they are diamagnetic, so they don't have show magnetism. Now we come to the next one. That's n equals 2. N equals 2 is the quantum number 2. That's the second period in the periodic table. The first period is quantum number 1. The second period is quantum number 2. The third period, quantum number 3. That would be this here. The fourth period, quantum number 4. This would be this. 5, 6, and 7. Okay? So far, 7 periods is enough to describe all the elements that we have so far, or that we know of. And so we go now to the second quantum number, second period. The first element is lithium. Lithium has 3 protons, is element number 3. So if it has 3 protons, it's got to have 3 electrons to be a neutral atom. That means we have the 1s. The 1s2 is filled. Okay? That means the 1s orbitals are filled now. And so we have a helium configuration that must be 1s2. Helium, we could write here in parentheses, instead of pointing this out, we could write here helium and then have an electron. Or we say this is helium in square parentheses and then 2s. This makes not much sense at the moment because it's not a whole lot writing. If you write 1s2 instead of helium, you have the same number of symbols or writing that you have to do. You have the square bracket, helium, square bracket, so you might as well write 1s2, okay? But if you get higher up here, for example, to here, and you want to describe rubidium, then you have to fill all these electron levels, these orbital levels, till you go to the 5th period, and so you would write krypton in parentheses, and then go with the higher electrons and keep going. So we will get the hang of this in a second. So that means the 2s2 has to be filled with 1 electron magnetic. Beryllium element number 4, beryllium here. So we have 4 electrons. We have the 1s2 filled and the 2s2, but now we come to the 2p, and this is with the next element is boron. Boron is element number 5. Boron here, element number 5. And so we have 1s2, 2s2, that's filled. Now we start filling the p1. So now the important part comes that we have to apply Dog's rule, Hunt's rule. Hunt me is German, means dog actually, okay? I'm not going to go into that television thing there, okay? This guy with dog, you ever seen this guy? Okay, so now you remember Hunt's rule, okay? All right, so boron has 1 unpaired electron. That would be paramagnetic. And now we come to carbon, element number 6. So you fill the second p orbital, that's the px, that's the py. And when you come to nitrogen, you fill the third p orbital, px, y, c. You fill this, and you fill them with parallel spin. So this here has a stronger shows stronger magnetism than this here, for example, because here you have 1 unpaired, here you have 2 unpaired, and if you go 1 higher to nitrogen, which is the next element, you have 7 electrons. So this is has stronger magnetism because you have 3 unpaired electrons. The configuration would be then 1s2, 2s2, 2p3. Okay, you see that? It doesn't tell you if you have 2p3 that they are unpaired. You need to know that. Right? You need to fill first parallel spin and then anti-parallel spin, and that's what you do now if you come to element number 8, oxygen. You start filling, filling that 2px, the second one goes in here. So then you have now 2p4. Fluorine is 2p5, you fill this here. And neon is 2p6. And now you have a filled orbital in n equals 2. And so you have helium and neon. We have seen that they have helium and neon, they have filled orbitals in that quantum number. The quantum number, the orbitals of the quantum number are filled. And people use slang, and they say there's a filled shell, filled electronic shell. There is no shell. Shells are in the sea, okay? There are no electronic shells. This comes from the understanding of the wonderful Bohr model, which is very important, that we have these concentric things, orbits around the nucleus, which is not true. Okay, so we can't talk about a shell if we have p orbitals. So they call it even the p shell. All right, and so every now and then it will slip even out of my mouth because this is chemistry slang. Yeah, it's totally wrong, but it's accepted, and everybody knows what we mean. All right, so this is filled orbitals in that quantum number. That would be the filled 2 shell here. Okay, the quantum number 2. All right. So the interesting thing is, if you go further and further, you come to the next shell, and you fill the. See, you come to the next quantum number, to the orbitals of the next quantum number, and fill them up, and then you end up again with this stable configuration. And that stable configuration, you see, is helium, neon, argon, krypton, xenon, radon. These are noble gases. Because there you can't add any more electrons. This is a very, very stable, a closed shell configuration. That is, the orbitals are filled. And so these, until the 60s, mid-60s, everybody thought these are noble gases. They don't react with anything. They are noble. And along came Professor Neil Bartlett, one of my colleagues here, whom I know quite well. Unfortunately, he passed away 4 years ago, and when he was a relatively young man, he came here as a young professor, and he reacted them with halogens under very tough conditions, and he made then these noble gas halogens, all kinds of different halogens, and so with this he proved the people that they were wrong, that he proved them wrong, and he should have won the Nobel Prize for this incredible discovery, and he became very, very famous. He won many prizes for this, but he didn't win the Nobel Prize, unfortunately, and I don't know why. He should have won it, and he passed away 3 or 4 years ago, and unfortunately, they don't award a posthumous award for the Nobel Prize. You have to be alive to get it, okay? You can't get an element named after you when you're dead, but you have to be alive. Actually, that was one of the conditions in the old days. But I show you an exception about this. The exception is this here, Seaborgium. Where is it? There it is, okay? We talk about this in a much later lecture. So the noble gases are not that noble if you hit them hard enough with halogens, okay? You make some very, very interesting compounds. So the theoreticians can now calculate this, and they show you exactly why. So let's think about this. So you have nitrogen. I give you that other table here. There comes a chem quiz, and we have nitrogen, oxygen, and fluorine, okay? And we want to flip an electron in the electronic configuration. And I want to know from you which one of the following, when I flip an electron, does not change its energy at all. Is it nitrogen, oxygen, or fluorine? Nitrogen, oxygen, or fluorine? Try to flip an electron and don't break any rules, okay? Why don't you answer that? If I flip an electron either here or here or here, it will not alter the energy. In this case, the ground state energy. Let's have a look at this. Okay. Why don't you discuss this with each other? Try to give me the right answer, some of you at least. I don't tell you. I don't tell you. Let's see if the neighbor can talk you out. Or if you're strong enough in your opinion that you say, no, no way. That's the whole point of a scientific discussion. What did you have? So you could flip this one. Would that be allowed? Oh, no, don't do that. Insist. Okay, so let's see. What's the rule called? Dog's rule, okay? You just can't go and flip electrons you like as much as you like. You have nitrogen. You flip that electron. That's not possible. It's not allowed, okay? It has to be parallel spin, so you can't flip the electron. Actually, you will need some energy to do that. There are possibilities. But for you, that's not allowed at this point, okay? It would go in a different energy state. Now, this one, oxygen, the same thing. You start filling this, you would have to flip this one here. It's not allowed. Okay? Hund's rule, okay? Dog's rule. Now, if you do the fluorine, we actually don't know if they're up or down, okay? They could be all down or could be all up, we don't know. Statistically distributed. But it really doesn't matter if this is up or down, it's the same thing. And it's allowed to do that, you're allowed to do that, all right? So with this, you were so close and then you just abandoned your solution. That's no good. All right, so the solution is F. See that? This is the only one you could flip here and does make a difference. If it's up or down, it doesn't know if it's up or down, actually. Yeah. All right? Good. So this was the solution. Don't let me trick you. All right? There comes another one. Who knows what an anion is? Okay, let's do something. Lights, please. Lights, and I need a strong guy. So I'm the nucleus, and I'm hanging on to my electron here, all right? Please, be strong. So he's going to ionize me now. Not annihilate me, he's ionizing me. So what would he have to do? Why don't you, I always point towards the door. When we go to state 0, to E equals 0, he's going out the door. So he has to ionize me. Would you need ionization energy? Is this energy that I put into the system? Yes, because I have the energy that this thing has here is the level energy, okay? You know Bohr's equation. We talked about this many times. So you'd have to take this away from me. Go for it. Oh, now run. So I'm ionized now. Now, I could have many other electrons around me, but he took one away. So what's my charge? +1. Now let's do the opposite. Say, there are elements that attract electrons. They have an affinity towards electrons. And so When he comes closer to me, I will grab it and I will release energy. Okay, come on. So now I'm a neutral. Let's wait. Wait. I'm a neutral atom. Okay, I have all kinds of electrons around me. I'm neutral. They go in orbit and in orbitals. So now comes another electron, and I have electron affinity. So there it comes. So thank you. Okay, so I have energy. I released energy. Now I have this extra electron. What's my charge now? Negative, okay? So what am I now? Say again? Anion, thank you. Okay, anion has an extra electron. Thank you very much. What's your name again? Jimmy? Okay, thanks, Jimmy. Okay. So you have learned what an anion and what a cation is, and you have learned, again, we repeated what ionization energy is. And the second thing is electron affinity. You learned what electron affinity, and we will write this a little later, okay, in the next lecture, electron affinity. But you needed this to know it. And now we are not in the ground state. We have a configuration, helium. What could you see? I write helium in square brackets. What does that mean? 1s2, okay? I could have written 1s2, but that way you get used to it. So I have 2s2, 2p5, 3s1. Which species could have this configuration? Could it be fluoride minus? Could it be sodium? Or could it be sodium plus? This configuration. So that's an excited state, possibly an excited state configuration. One electron might have gone in a higher state, or two maybe. All right? So first of all, you need to count the number of electrons that you have, and then you have to make some sense out of it. Okay, let's go. Let's see what you think. Everything's here. Is it here? Yeah, it is here. And obviously, it's not a ground state here. You took one electron and put it in a higher state, maybe. Maybe. The first thing I would do, count the electrons. Then you can exclude a couple of, maybe one or two, I don't know. Okay. It's all about conviction, okay? So, how many electrons do you have there? And in the valence shell, this is the valence shell, the valence orbitals. This is the outermost orbitals. These are the outermost orbitals. How many you have in the outermost orbitals? Okay, the others, they're always the same. So how many in the outermost orbitals? One at the moment. Yeah. And how many total, if you just, everybody has those, how many total? Okay, why don't you start counting and have a look here how many this one, for example, has? This one here, and how many this one has? And what was the other one? No, oxygen doesn't care. This one here, if I have a fluoride, and sodium, this one, if I take one away. All right? So, discuss this with each other, and be firm in your opinion. You got it, huh? Don't have enough buttons on the thing, huh? Okay, excellent, excellent. Nobody talked you out of it, except 3%. Good. So there was the usual little bit of a trick question, or a trick answer maybe. So sodium you can exclude, okay? Sodium has in the outermost orbital so this is the 1s2, you have 2, 4, 6, 8, 9. And what did I ask you before? Let's see. What did I give you? I gave you 2, 7, 8. So that can't be, all right? You have one electron too much. So the sodium is not it, okay? So the next one would be, if we look at sodium plus, if we lose that one here, or we take one out of here, okay, sodium plus, we take one out of here, then we have a 2s2, 2p5, 3s1. Yeah, sodium is the answer, okay? If we have fluoride, we add one here. So we could add it here, because it's an excited. It's not a ground state level. It's an excited. There's nothing can speak against this adding it here. Hund's rule applies for ground states, if we do ground state, okay? So you add it here. With this, you have then a 2s2, 2p5, 3s1. There you go. This seems to be the same than this one here. And with this, you have the right answer. There you go. Okay? All right? And so you insisted that your answer was right. That's excellent. And if you knew that both answers were right, then it was even better. Good. So we're talking about the periodic table in the next couple of lectures. And what's so periodic about the periodic table? And let me give you some overview here. I hope it comes here. Yeah, okay. So we already talked a little bit about ionization energy, but I would like to talk about the founder of the periodic table, about Dmitry Ivanovich Mendeleev. He was a Russian. He lived in the 19th century, and he was a professor at St. Petersburg, and he did a lot of experiments with compounds which belong compounds and their atomic weights and their properties. And he correlated the atomic weights and the properties to each other, and he studied 63 compounds. He found some periodic behavior. So they behave similarly, and they behave similarly, and they behave similarly. And he came up with the modern periodic table. We're still using this periodic table. You have built a lot more elements into it. But you have to imagine, Mendeleev, he had no idea that there were electrons, and he had no idea that there was a nucleus, okay? And he developed that periodic table and says there's certain periodic behavior and certain group behavior, and he came up with, this was sort of his first periodic table. And at the same time, there was a guy in Germany, of course, I have to talk about the German. Germany, his name was Lothar Meyer, and he had a textbook for Chem 1A. I think they weren't teaching then Chem 1A. And this textbook included sort of an abbreviated form of something like a periodic table, and he published, they wanted to publish this then in 1868, and of course it took forever for the journal to get this because they didn't have Twitter, they didn't have email, and all this kind of stuff. And so they had to send it by, and snail mail was even pretty slow. So they had to send it to the publisher, and they had to be reviewed, and then it finally got accepted. And when the paper came out, that was in 1860, 1869, 1870, 1869, Mendeleev's paper was already out. So he is the founder of the modern periodic table, and we still to this day use the periodic table. Very sophisticated version, though, of it, but it still holds true. He could not have known all this, but it was just amazing how he arranged some of these first elements. So there, if you go to St. Petersburg in front of the University Institute, there is this first periodic table. And I had the pleasure to give a lecture there many years ago, and was very impressed by this whole setup that he had. He had, just like we have here in the back, there was a lecture hall, bigger than that actually. In the back he had his living quarter, and him and his wife lived in the back in the apartment there. And in the other side of the back, he had his laboratory. So if he woke up at 3 o'clock in the morning and said, oh, I have a good idea, he walks over to his laboratory, checks it out and sees if it works. That's ideal working conditions, okay? And the interesting thing at the time, as I said, they didn't have internet and they didn't have Facebook and Twitter and so on. They actually needed to talk to each other, okay? And what was there, he had lots of colleagues, and some of them famous and some of them not so famous. They became famous later. He had them over. They drank and ate, and the guys were discussing science, and some, I don't know if there were women at the time discussing science, probably they were listening. That changed very rapidly then with Marie Curie and other very famous scientists in the beginning of the 20th century. But at the end of the evening, they were signing the tablecloths. Everybody was signing it. Some of them were not very famous, and others were famous already. And so the daughter and the wife, they embroidered this tablecloth with all these famous names. So there's these names embroidered on the tablecloth. If you get there, look at the tablecloth. You will, if you understand a little bit about chemistry and physics, you will be in awe who was all there eating and drinking. And at times they went out there when they had an idea. They all went out to the lab and did something together and seen that it worked or didn't work. Ideal working conditions, but no separation of private and professional life. So coming back to Mendeleev, he is the founder of the periodic table. And so this is what we sort of, here is the skeleton of the periodic table. I already told you we have these periods. They go from left to the right as you fill the orbitals in each of the quantum number, the main quantum number 1, 2, 3, 4, 5, 6, and 7. And you also have groups. If you look at this, for example, this would be the group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Forget these numbers now here. The very modern books a couple of years ago, 3-4 years ago, IUPAC changed that. And so you see you have both of them up here in the periodic table. You see the red ones are the numbers going through from 1 to 18, and the other ones going from 1A, 2A, and then the 3B, and so on. This was the old grouping of it, okay? So why is that? So if we go, for example, to the second period, we have the 2S1, 2S2, 2P1, 2P2, 2P3, 2P4, 2P5, 2P6, okay? All right, so we are at the end of that period. We have the quantum number 2, we have filled the orbitals. Now we come to quantum number 3. So you have S, 3S1, 3S2, 3P1, 3P2, 3, 4, 5, 6, 7. And then we should have filled the 3D, okay? But the 3D are actually, the 4S is lower in energy than the 3D. So we start with the 4S, 4S1, 4S2, and then we fill the 3Ds, and then we come to the 4Ps, because the 3Ds are have a different level. I showed you this when I talked about the different levels. So, and you go on the 5S, and the 4Ds are below the are above the 5S, so the 5S are lower. Then you have the 4D, then you get the 5P. And when you come to the 6S, you have another group. They're the 4F, they are lower, okay? And you start filling them in the 6th period, you fill the 4F electrons, actually, okay? So, and these are called the F elements, and the 4F elements are called the lanthanides, and the 5F elements, which are filled after actinium, are called the actinides. If you look at the alkali, the first period are the alkali metals, all right? And this, if you could have the periodic table here, please. The one on the left. So there's lithium, sodium, potassium, rubidium, cesium, and francium. Now, if you look at the outermost orbitals, they have all the same configuration, because the orbitals of the lower quantum number, the one lower quantum number, are filled here. And then you get the outermost orbital. So this would be a 5s1, and this would be a 5s2. That would be 4s1, 4s2, 3s1, 3s2, 2s1, 2s2. You see that? And if you have chemical reactions and binding, It's essentially the outermost orbitals which are involved in the binding. Not in all cases, but you can take it sort of as a rule of thumb, for you especially. The outermost orbitals are, and they are called valence orbitals, and the electrons in there are the valence electrons. So what this tells you, essentially, since you have the shielding of the inner electrons, the outer electrons are the ones who do the binding. Since you have the same orbital, the same electronic configuration, just in a higher level, like 4s1 and 5s1 and 6s1, this would be 4s1 would be potassium, 5s1 would be rubidium, 6s1 would be cesium. You see that here? Okay. They have similar chemical behavior. That's we call this from, if they have the same electronic, most electronic configuration, we call this a group. They are in the same group here. This is group 1, group 2, and so on till you get to group 18. And the elements in group 1, for example, sodium and potassium, behave somewhat similarly. Or potassium and rubidium behave somewhat similarly because they have the same constitution of valence electrons, just in a higher energy level. I say somewhat. They don't behave totally similarly, okay? But in many of the behaviors, you can extrapolate from the homologue. So we call these higher states homologues, and we call, if you look at one group here, these are a group of homologues. That means they have homologous behavior, okay? And so if you have a lighter homologue and you look at the homologue that is heavier, so there is some conclusions of similar behavior you can draw from that. And this is true with all the groups here, okay? So this is the homologue behavior within one group because of the electronic constellation of the outermost orbitals. Now you have here the table of elements here. These are the alkali metals. These are the alkaline earth metals. These are the transition metals. These are the transition metals. And then you have here, we call them poor metals. Actually, they are not poor metals. They are neither really metals, nor are they non-metals. They are metalloids. Semiconductors are, for example, belong to this group. You see germanium and antimony and gallium. These are semiconductors. Arsenic also. And this group here has partially metallic behavior and partially non-metallic behavior. And then you come to the non-metals, and then you come to the so-called noble gases. Here are the lanthanides and the actinides. And this is the IUPAC table, how it looks at the moment. You have from 1 to 18 here, and element number 111 is already named. This is rentgenium. 112 will be named soon. And you have a total of 111 confirmed elements, and very soon a total of 112, and very soon a total of 114 confirmed elements. Okay? And with this, we talk more about this the next time, and the behavior of the elements in the periodic table, and I see you on Friday.